Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Settle into a comfortable position. Allow your body to rest in whatever way feels natural. There is nothing you need to do right now, nothing to solve, nothing to anticipate. This is a space for gentle attention, for quiet curiosity, for letting the mind soften as the universe stretches far beyond the present moment. Tonight, you are not being guided toward an ending that arrives suddenly, not toward collapse, not toward catastrophe. Instead, this is a story of gradual change, of patience written into the fabric of reality, of a universe that does not shatter but slowly ages, cooling, expanding, and gently fading over unimaginable spans of time. The universe you inhabit right now is active and luminous. Stars are being born, galaxies are colliding, light travels freely across vast distances, energy flows from hot places to cold ones, and time feels full of events. But none of this is permanent, not because something goes wrong, but because change itself is built into the laws that govern space, matter, and energy. From the very beginning, the universe has been evolving, not racing toward an end, but following a slow thermodynamic path, a path shaped by expansion, by gravity, and by the quiet tendency of energy to spread out. When cosmologists speak about the future of the universe, they do not describe a final moment, they describe eras, each lasting far longer than the age of the universe so far, each defined not by drama, but by subtle shifts in what is possible. In these distant futures, nothing violent needs to happen. There is no single moment when everything stops. Instead, processes simply run their course. Stars use up their fuel, matter settles into lower energy states, temperature differences even out, and activity becomes increasingly rare. This is not a story meant to provoke fear, it is not a warning, and it is not a countdown. It is a description of rest on a cosmic scale. To understand this future, it helps to let go of ordinary time. Seconds, minutes, years. These units lose their meaning when stretched far enough. The universe measures its future in millions of years, in spans so large that language itself begins to feel inadequate. Yet these timescales are not abstract to physics. They arise naturally from equations that describe how stars burn, how particles interact, how energy flows, and how space itself expands. The same laws that allow the universe to shine also ensure that it will eventually grow quiet. This does not mean the universe is failing. It means it is following its nature. Everything that exists today does so because conditions once allowed complexity to form. Dense clouds collapsed into stars, stars forged heavier elements, planets assembled from cosmic debris, and chemistry found ways to become intricate. But complexity requires gradients, differences in temperature, differences in density, differences in energy. Over time, these differences diminish. Energy spreads out, matter disperses, and the universe moves toward balance. This movement is not hurried. It is extraordinarily slow, so slow that from a human perspective it feels almost frozen. And because it is so slow, it is gentle. There will be no sudden extinguishing of the sky, no instant darkness, no moment when the universe realizes it is ending. Instead, the cosmos will gradually shift from being a place where new things happen to a place where fewer and fewer things occur. Stars will become rarer, galaxies quieter, interactions more infrequent. Eventually, the universe will reach states where change is so minimal that entire eras pass without anything noticeable unfolding. This is what physicists mean when they talk about the universe having a future. Not a final scene, but a long, tapering quiet. And within this immense timeline, human life occupies only a fleeting instant, a brief glow within a much larger story. Recognizing this does not make existence meaningless. If anything, it places it gently into perspective. You are here during a luminous chapter, a time when stars still shine brightly, when galaxies still teem with motion, when energy still flows in ways that allow thought, observation, and wonder. The future of the universe does not rush toward us. It recedes from us, always remaining far beyond reach. So there is no urgency here, no need to hold on, no need to prepare. You can simply observe from a place of calm. As this journey unfolds, you will move through ideas that stretch across deep time. But you do not need to keep track of them. You do not need to remember details. You do not need to follow every explanation. The goal is not comprehension in the ordinary sense. It is familiarity, a gentle sense of how the universe behaves when given enough time. Let the scale of it all do the work. Let trillions upon trillions of years dissolve the sharp edges of thought. Let distance soften concern. Let inevitability feel like reassurance rather than loss. The universe is not rushing toward its end. It is slowly relaxing into it. And as you rest here, breathing quietly, supported by stillness, you are free to drift alongside that immense calm, knowing that nothing in this story asks anything of you. There are no sharp conclusions waiting ahead, only gradual fading. Only patience, only quiet transitions. You may notice your thoughts becoming slower, less insistent, as the idea of deep time stretches them thin. That is natural. This is what happens when the mind contemplates a universe that does not hurry. Stay here for a moment longer, resting at the threshold of an unimaginably long future, where light slowly thins, where motion grows rare, and where the cosmos itself seems to breathe more slowly. When you are ready, the journey can continue. Stars are born quietly, not in explosions, not in moments of sudden creation. They emerge slowly, from cold, from darkness, from regions of space that seem, at first glance, almost empty. Across galaxies, vast clouds of gas and dust drift for millions of years. These clouds are thin by earthly standards, yet they are enormous in size, spanning many light years, containing the raw material for thousands, sometimes millions of stars. Within these clouds, gravity works patiently. There is no urgency, no schedule to keep. Tiny variations in density become important over time. A slightly denser region pulls in a little more matter. That added mass strengthens its gravitational pull, drawing in still more gas. This process is slow, almost imperceptible on human timescales. As gas accumulates, pressure increases, temperature begins to rise, the cloud contracts further, flattening, fragmenting, breaking into smaller regions where gravity gains the upper hand. Eventually, deep within these collapsing pockets, conditions change. Hydrogen atoms move faster. Collisions become more frequent. Temperatures climb to millions of degrees. And when the core grows hot and dense enough, nuclear fusion begins. Hydrogen nuclei merge. Energy is released. Light is born. A star has entered the universe. This process is still happening today, in spiral arms of galaxies, in distant nebulae, in places where gas remains cool and plentiful. But even now, the universe is no longer as fertile as it once was. Star formation reached its peak billions of years ago, during an era when galaxies were rich in cold gas. When collisions between galaxies were common, when turbulence stirred matter into dense, star-forming regions. Since then, the rate of stellar birth has been declining. Not abruptly, not dramatically, just steadily. Galaxies age, gas is consumed, some is locked away inside stars, some is expelled by stellar winds and supernovae, some drifts beyond the reach of galactic gravity. Each generation of stars leaves less raw material behind than the one before. Galactic evolution plays its part as well. Over time, many galaxies settle into quieter configurations. Their spiral arms fade, star-forming regions shrink, motion becomes more orderly, less chaotic, collisions become rarer as cosmic expansion increases the distances between galaxy groups. The universe grows larger, but less crowded, and with that expansion comes a subtle cooling. Space itself stretches, radiation loses energy as it travels, temperatures drop, fraction by fraction. Cold gas becomes harder to compress, harder to ignite. Star formation does not stop because the universe chooses to end it. It slows because the conditions that allow it gradually disappear. In this long future, one class of stars becomes increasingly important: small, cool, red dwarf stars. These stars are modest in mass. They burn their fuel slowly, carefully, conservatively. A red dwarf can shine for trillions of years, far longer than stars like the sun. While larger stars live fast and die young, red dwarfs persist. As the universe ages, these small stars dominate the stellar population. They form when little gas remains, when conditions are no longer ideal, but still just sufficient. Their light is faint, often invisible to the human eye, but steady. For an unimaginably long time, the universe becomes a place lit mostly by these dim, patient stars. The night sky, if anyone were there to observe it, would look different. Bright blue stars would be rare, massive, short-lived stars almost non-existent. Instead, the cosmos would glow softly, with sparse pinpricks of red light, separated by vast stretches of darkness. Time stretches further, trillions of years pass. Even red dwarfs eventually exhaust their fuel. Hydrogen becomes scarce, fusion slows, light weakens, but still there is no moment of finality. Each star fades on its own schedule. Isolated, unobserved. By this stage, stellar births have become extremely rare. Cold gas clouds still exist, but they are thin, diffuse, scattered. Gravity struggles to gather enough material in one place. Pressure never quite reaches ignition. A cloud may contract for millions of years, only to disperse again, stretched by tidal forces, heated slightly by passing radiation. Star formation becomes a quiet exception rather than a common process. Then eventually, even those exceptions cease. There is no ceremony, no universal signal, just a time when the star forms, not the last star to shine, but the last one to be born. From that moment on, the universe enters a new state. Existing stars continue their long lives. Some still burn steadily, others begin their slow decline, but nothing new ignites. The stellar population becomes a closed set, a finite collection of lights slowly aging together. Galaxies drift onward, their shapes becoming less defined, their contents thinning. Gravitational interactions still occur. Stars orbit galactic centers. Remnants pass each other silently. But the cosmos grows quieter. The sky thins, not suddenly, not dramatically, just patiently. Light sources grow fewer, distances grow larger. Where once galaxies blazed with billions of stars, now they hold scattered embers. The universe does not notice this transition. There is no awareness, no threshold crossed. Yet from a physical perspective, something profound has changed. The era of creation has ended. From this point forward, the universe becomes a place of inheritance rather than birth. Everything that will ever shine already exists, and it will all, in its own time, begin to fade. There is no rush. Stars continue to glow for trillions upon trillions of years, their light traveling across space, growing dimmer as expansion stretches each photon. Galaxies grow quieter, more spacious. Time itself seems to slow, not because it changes, but because fewer events occur within it. The cosmos enters a long twilight, a universe where new light is no longer being created, where the future consists only of gradual transformation, of aging, of cooling, of rest, and still, everything remains calm. The slowing of star formation is not only a matter of fuel being used up, it is also shaped by how galaxies themselves change with time. In the early universe, galaxies were crowded environments. They interacted frequently, passing close enough to tug at each other gravitationally, stirring their gas, compressing clouds, triggering waves of star birth. These encounters were not violent in the way the word is often used. They were slow, drawn out over hundreds of millions of years, yet they were effective at turning quiet gas into luminous stars. As the universe expands, this behavior changes. Distances between galaxy groups increase, encounters become less frequent, and when they do occur, they tend to be gentler, involving galaxies that already carry less gas than before. Within individual galaxies, internal motion also settles. Young galaxies are turbulent. Their gas flows chaotically. Shock fronts ripple through their disks. Density fluctuations are common. Older galaxies grow calmer. Gas settles into thinner layers. Rotational motion becomes more orderly, and the random compressions that once sparked star formation happen less often. Even when gas is present, it may remain too stable, too evenly distributed, too warm, to collapse efficiently. In this way, galactic aging quietly suppresses the birth of new stars. At the same time, the universe itself continues to expand. Space stretches between galaxies, and with that stretching comes isolation. Clusters that are gravitationally bound remain together, but beyond those regions, galaxies drift farther and farther apart. Eventually, distant galaxies cross a horizon where their light can no longer reach one another. From any single location, the observable universe grows smaller, not because space shrinks, but because expansion outpaces light. This isolation deepens the quiet. Star formation is not only about having gas, it is about having neighbors, perturbations, interactions. As the universe grows larger and emptier, these influences fade. Over trillions of years, the remaining star-forming regions become rare pockets, surrounded by immense volumes of nearly empty space. When stars do form in these late times, they tend to form alone, no clusters, no crowded nurseries, a single red dwarf igniting quietly within a thin cloud, shining faintly. Almost unnoticed, these late-born stars live extraordinarily long lives. Their nuclear reactions proceed slowly. Their luminosity remains low. They sip their fuel rather than consuming it. For a time, these stars offer the last new light the universe will ever produce. But even this era has an end. As expansion continues, as gas thins further, as background temperatures drop, the conditions required to initiate fusion finally disappear, not abruptly, but asymptotically. There is no clear moment when star formation is officially over. Instead, the probability of it occurring approaches zero. Millions of years pass without a single new star forming, then billions, then trillions. Eventually, the universe enters a state where star formation has effectively ceased. Every star that will ever exist already does. What remains is a finite population, distributed unevenly, aging independently. Some stars are still bright. Others have already begun to fade. Many orbit the quiet centers of galaxies. Others have been ejected by gravitational interactions. Drifting alone through intergalactic space, these solitary stars burn their fuel in isolation, unseen, unaccompanied. There are no new stellar neighborhoods forming around them, no generations following behind. Each star becomes a closed system, moving steadily toward equilibrium. The night sky, viewed from any surviving vantage point, grows thinner. Where once the sky was crowded with points of light, now there are gaps, vast, dark intervals. The remaining stars are separated by distances so great that their light takes millions of years to cross the space between them. As time stretches further, even that light weakens. Photons lose energy as space expands. Their wavelengths lengthen, their colors shift toward the red, toward invisibility. The universe does not go dark all at once. Instead, brightness becomes rare. The sky becomes a canvas of darkness punctuated by a few dim embers. This thinning happens patiently. There is no moment when the last bright sky is noticed. No observer to mark it, only gradual change, layer upon layer of quiet. By the end of this era, the universe has changed its character. It is no longer a place where structure is actively built. It is a place where structure is slowly unwinding. The flow of energy that once powered complexity diminishes, yet nothing collapses, nothing breaks. Stars continue to shine for as long as their physics allows, obedient to the same equations that created them. They burn, they cool, they fade, one by one, and when the last of these stars finally exhausts its fuel, the universe does not react. There is no signal, no transition, just a quiet continuation. The cosmos enters a long twilight, a universe where light still exists. But only as inheritance, not as creation. A universe where nothing new ignites, and everything that remains moves slowly toward rest. When this process is complete, the era of stars has ended. Nothing dramatic marks its passing, only patience, only time. When stars finish shining, they do not vanish, they remain, changed, condensed, quiet. The universe does not discard its stars when their light fades. It keeps their cores, their mass, their gravity. What follows the age of active starlight is an era shaped by remnants, objects that no longer produce energy through fusion, yet still persist for spans of time that dwarf the lifetimes of stars themselves. To understand this era, it helps to remember what a star truly is: a balance. Gravity pulls inward, pressure from nuclear fusion pushes outward. As long as that balance holds, a star shines. But when fuel runs low, or conditions shift, gravity slowly wins. For many stars, especially those similar in mass to the Sun, the outcome is gentle. As fusion slows, the outer layers drift away, expanding outward into space, leaving behind a dense core. This core is called a white dwarf. Despite the name, it is neither bright nor large. A white dwarf is roughly the size of a planet, yet it contains a mass comparable to that of the Sun. Matter inside it is compressed to extraordinary densities. Electrons are forced into close proximity, supporting the star not through heat, but through quantum pressure. A white dwarf does not burn, it does not fuse, it simply cools, slowly, steadily, over trillions of years. At first, it glows faintly from residual heat, a quiet ember left behind after a stellar fire. Over time, that heat radiates away. The surface temperature drops, light becomes dimmer, redder, longer in wavelength. Eventually, after spans of time longer than the current age of the universe, a white dwarf becomes so cool that it emits almost no visible light at all. At that point, it is sometimes called a black dwarf, not because it is violent or destructive, but because it has reached thermal quiet. No black dwarfs exist yet. The universe is not old enough. They belong to a future so distant that even the oldest stars have not had time to cool that far. Alongside white dwarfs are neutron stars. These form from stars much more massive than the Sun. When such stars exhaust their fuel, gravity overwhelms the core with extraordinary force. Electrons and protons are crushed together, forming neutrons. The result is an object only a few kilometers across, yet heavier than the Sun. Neutron stars are extreme, dense, compact. They rotate, sometimes rapidly. Their magnetic fields can be intense. Early in their lives, neutron stars can emit radiation, beams of light sweeping through space. But even these emissions fade. Rotation slows, magnetic fields weaken, energy dissipates. Over time, neutron stars become quiet, cold, dark. They remain silent witnesses to a more active past. Then there are brown dwarfs, objects that never quite became stars. They form when a collapsing cloud gathers enough mass to glow faintly, but not enough to ignite sustained fusion. Brown dwarfs are common. They drift through galaxies, often unnoticed. They begin warm, but cool steadily. Like white dwarfs, like neutron stars, they lose energy without replacing it. In the deep future, brown dwarfs become some of the coldest objects in the universe. These remnants populate the cosmos. White dwarfs, neutron stars, brown dwarfs, all moving through space, all obeying gravity, all slowly approaching thermal equilibrium. The universe during this era is no longer defined by light being produced. It is defined by light being preserved. Energy exists, but it is trapped in forms that can no longer do much work. This is where entropy becomes important. Entropy is not disorder. It is the spreading of energy. In a young universe, energy is concentrated. Stars burn hot, surrounded by cold space. This difference allows things to happen. But as stars fade, as remnants cool, energy spreads more evenly. The temperature differences that once powered complexity diminish. Each remnant radiates its heat into the surrounding universe, photon by photon. Over enormous spans of time, space itself remains cold, but even that cold background grows warmer in comparison. Eventually, remnants approach the same temperature as their surroundings. At that point, radiation slows further. Cooling becomes asymptotic, approaching stillness without ever quite reaching it. In this era, motion still exists. Stars orbit galactic centers. Remnants pass one another at great distances, but interactions are rare. Galaxies themselves have changed. Many have merged into larger structures. Others have drifted beyond reach. Within bound systems, stars and remnants continue their slow dance. Yet without new energy input, nothing new emerges. No new chemistry, no new structures, just gradual fading. The universe transitions fully from being light-producing to being light-preserving only. Everything that shines does so because it once shone brighter, and every glow weakens with time. White dwarfs become black dwarfs. Neutron stars cool toward invisibility. Brown dwarfs fade into the background. The cosmos fills with objects that are still massive, still present, but almost impossible to see. From any hypothetical vantage point, the universe appears nearly dark, not empty, but subdued. Motion continues. Gravity still shapes trajectories, yet activity fades, time stretches, changes occur, but so slowly that millions of years pass between noticeable differences. The universe grows simpler, quieter. This is not an ending, it is a settling, a long exhale after the age of stars, and still, everything remains calm. As this era continues, the most important change is not what exists, but what no longer happens. No object in the universe is able to generate new energy through fusion anymore. Every source of light that remains does so only because it still holds residual heat. This heat leaks away slowly, through thermal radiation. Every white dwarf, every neutron star, every brown dwarf radiates energy outward, photon by photon, into surrounding space. This radiation is extremely weak, far weaker than starlight ever was. But over immense spans of time, even this faint emission matters. Each emitted photon carries away a small amount of energy, lowering the internal temperature of the object that released it. There is no mechanism to reverse this process, no fuel to reignite, no compression to restart fusion, no collapse to raise temperatures again. The direction is fixed, energy spreads outward, temperature differences diminish, entropy increases, space itself plays a role here. The background temperature of the universe continues to fall. As expansion stretches radiation to longer and longer wavelengths, early on, remnants are warmer than their surroundings, and so they radiate efficiently. Later, the difference narrows, cooling slows. Eventually, a white dwarf becomes nearly the same temperature as interstellar space, then intergalactic space. At this point, change becomes extremely subtle. Cooling continues, but at a pace so slow that entire eons pass with almost no measurable difference. This is what it means for an object to become colder than space itself, not colder than absolute zero, but colder than any nearby environment. At that stage, thermal equilibrium dominates. The remnant is no longer a source of usable energy. It cannot drive processes. It cannot power reactions. It simply exists. Neutron stars follow a similar path. Their initial internal heat is immense, but they are efficient radiators. Over billions, then trillions of years, they cool. Their surfaces grow dark. Their emissions fade into near silence. Brown dwarfs cool fastest of all. Without sustained fusion, they radiate away their heat steadily from the moment they form. By the deep future, they become some of the coldest massive objects in existence. Throughout this era, entropy steadily increases. Energy becomes more evenly distributed, less concentrated, less useful. This does not mean chaos, it means uniformity. The universe moves toward a state where no region is significantly hotter or colder than another. Without gradients, there is no flow. Without flow, there is no work. Motion still exists, but it is repetitive, predictable. Stars and remnants orbit along paths set long ago. Galactic structures remain bound where gravity allows, but nothing new emerges. No new chemistry, no new structures, no new complexity. The universe has transitioned fully into preservation mode. Light exists only because it was created in the past. Motion exists only because it was set in motion long ago. Every process trends towards stillness. The cosmos becomes filled with massive objects that are effectively invisible, drifting silently through vast volumes of near-perfect darkness. This era is long, incredibly long, far longer than the age of stars ever was, and when it finally completes, when remnants have cooled as much as physics allows, the universe is quiet, but not empty. It is filled with cold matter, sparse radiation, and immense stretches of space between everything. The age of remnants has reached its natural conclusion. Nothing dramatic announces it, only time, only patience, only calm. Black holes do not begin as endings, they begin as consequences. They form when gravity gathers matter so densely that no known force can halt its inward pull. In the universe of stars, black holes are relatively rare, but in the far future they become dominant. When massive stars exhaust their fuel, their cores collapse. If the mass is great enough, no stable remnant can form. The result is a region of space where gravity becomes extreme. Light cannot escape. Matter cannot resist. A black hole is born. At the centers of galaxies, much larger black holes already exist. Supermassive black holes, containing millions or billions of times the mass of the Sun. These giants grow slowly, by consuming gas, by merging with other black holes during galactic collisions. As the universe ages, galaxies merge, clusters settle, and matter sinks toward gravitational centers. Over immense timescales, black holes become the largest organized structures left. Stars and remnants gradually fall inward, either directly or through complex gravitational interactions. Black holes act as quiet anchors, not aggressive, not predatory, simply present. Matter that drifts too close crosses an invisible boundary and becomes part of the black hole's mass. Inside that boundary, physics as we know it no longer applies. From the outside, however, black holes are remarkably simple. They are defined only by mass, rotation, and electric charge. Everything else is lost to the interior. For a long time, black holes appear eternal. Nothing escapes. Nothing diminishes them. But this impression is incomplete. In the 1970s, physicists discovered something unexpected. Black holes are not perfectly black. They emit radiation. This radiation is extremely weak, far weaker than anything observable from astrophysical black holes today. It arises from quantum effects near the event horizon. Pairs of particles briefly appear from the vacuum. One falls inward, the other escapes. Over time, this process allows energy to leak away. This is known as Hawking radiation. The effect is extraordinarily slow. For a black hole with the mass of a star, evaporation would take far longer than the current age of the universe, far longer than the era of remnants. For supermassive black holes, the timescales are even greater, yet the direction is clear. Black holes lose mass, incredibly slowly, but inevitably. As they shrink, their temperature increases slightly. Accelerating the process, still the change is glacial. Eons pass, trillions upon trillions of years unfold. Black holes persist as the last structured objects in existence. Around them, space grows emptier, colder, darker. Eventually, long after stars have faded, long after remnants have cooled, black holes begin their final act. They evaporate, not explosively, not dramatically, but quietly. A gradual thinning, a slow release of radiation, until at last nothing remains, no mass, no gravity well, no anchor, just radiation diffused into space. When the final black hole disappears, the universe changes character once again. There are no large structures left, no stars, no remnants, no gravity-bound systems of significance, only particles, radiation, and vast emptiness. The universe becomes more diffuse than intuition allows. Darkness itself begins to fade, and still, everything remains calm. As black holes continue to dominate the remaining structure of the universe, their role becomes quieter, but more absolute. In earlier eras, black holes coexist with stars, with remnants, with glowing matter orbiting nearby. In the deep future, this context disappears. There are no stellar neighborhoods left, no bright disks of gas, no new material falling inward in dramatic displays. Black holes persist alone, surrounded by darkness, embedded in an increasingly empty universe. Their dominance is not active, it is passive. They do not shape their surroundings through light or radiation. They shape them through gravity alone. For vast stretches of time, black holes appear unchanged. They orbit one another slowly within the last gravitationally bound systems, sometimes merging, combining their masses, forming larger and larger black holes. These mergers are among the final energetic events in the universe. But even these grow rare. As space expands, bound regions become isolated. Once those regions settle into stability, nothing disturbs them again. Black holes then become the only long-lived concentrations of mass left. Yet even gravity is not eternal. The slow emission of Hawking radiation continues. This radiation is unimaginably faint. For a black hole with the mass of a star, the temperature associated with this radiation is far colder than the background of space. For supermassive black holes, colder still. At first, the black hole absorbs more energy from its surroundings than it emits, but the universe continues to cool. Eventually, the background temperature falls below the temperature of the black hole itself. From that moment onward, evaporation dominates. This transition takes an enormous amount of time, far beyond trillions of years. But once it begins, it never reverses. Each emitted particle carries away a tiny amount of mass, a fraction so small that it defies intuition. Yet over inconceivably long durations, these fractions accumulate. The black hole shrinks. As it loses mass, its temperature rises slightly, increasing the rate of radiation. Still, the process remains gentle. There is no sudden flare, no violent end. The black hole fades, just as stars once did. For the largest black holes, this fading takes longer than any other known process in the universe. They outlive stars, they outlive remnants, they outlive galaxies themselves. They become the final clocks of cosmic time. Eventually, even the last black hole completes its evaporation. What remains is not emptiness, but simplicity. The radiation released disperses into space. Its energy spreads thinly across expanding volume. There are no longer any massive structures capable of shaping large-scale behavior. No gravity wells deep enough to gather matter, no centers, no anchors. The universe enters a new phase, one defined not by objects, but by fields and particles. Space grows darker, but even darkness becomes less meaningful. With no light sources, with no observers, contrast itself dissolves. The universe has lost its final large structures, and still, time continues. Matter feels solid, permanent, reliable. Atoms hold together, molecules persist, objects endure. But this stability is conditional. It depends on forces that may not last forever. At the heart of every atom lies the proton, a particle that appears remarkably stable. In the present universe, protons do not decay. They persist unchanged for billions of years. Every atom you encounter exists because protons hold their identity. Yet some theories in physics suggest that this stability is not absolute. They propose that protons may eventually decay. Given enough time, not quickly, not noticeably, but over spans of time so vast that even black holes have already vanished. Proton decay is not something we have observed. It remains theoretical, but if it occurs, it would represent one of the final transformations in the universe. A proton is composed of smaller constituents, bound together by fundamental forces. In some models of particle physics, these forces allow extremely rare processes, so rare that a single proton might survive longer than trillions upon trillions of years, yet not infinitely. If proton decay occurs, it happens quietly. A proton transforms into lighter particles, such as photons and other fundamental constituents. The atom that depended on that proton loses its identity. Matter begins to dissolve, not explosively, not catastrophically, but gently, one particle at a time. Atoms that once formed solid remnants, white dwarfs, neutron star crusts, diffuse clouds of matter, begin to change. Their building blocks no longer hold. Structures loosen, then disappear. Matter does not vanish, it transforms. Mass converts into radiation and lighter particles. Energy spreads further into space. As this process continues, the distinction between matter and radiation fades. Everything becomes simpler. Fields dominate, particles move freely. Interactions become rare. The universe becomes increasingly uniform. There are no objects, only distributions, no surfaces, no boundaries, just space, energy, and time. This process unfolds over timescales that resist comprehension, each step separated by immense durations, each change almost imperceptible, and yet the direction is consistent. Structure gives way to simplicity, identity gives way to uniformity. Even here, uncertainty remains. Physics does not yet know whether proton decay truly occurs, or whether matter is absolutely stable. This uncertainty is not alarming. It is simply a reminder that the universe still holds unanswered questions. But if decay does occur, then this era represents the final dissolution of matter itself. Not an ending, but a smoothing, a universe exhaling complexity. By the time this process completes, there are no atoms left, no remnants, no black holes, only faint particles. Radiation and vast expanding space. The universe grows quieter still, and nothing resists the calm. As matter continues to thin, as particles spread farther apart, the universe approaches a state where structure itself becomes increasingly difficult to define. Even before any hypothetical decay completes, matter grows isolated, distances between particles increase as space expands, encounters become rare, interactions infrequent. Atoms that once formed dense remnants are no longer gathered together. They drift, separated by enormous volumes of empty space. If proton decay does occur, its effects unfold within this already quiet universe. Each proton, once stable beyond question, becomes a temporary arrangement, not fragile, but not eternal. The predicted lifetimes involved are immense, many orders of magnitude longer than the age of the universe today. A single proton may persist for numbers of years that are difficult to express even in words. Yet over such durations, even the rarest processes matter. When a proton decays, it does not shatter its surroundings. It does not trigger cascades. It simply changes state. The decay products move away at near the speed of light, carrying energy outward, adding to the diffuse background of radiation. The atom that depended on that proton loses coherence. Electron orbits no longer make sense. The structure dissolves. This does not happen everywhere at once. It happens sporadically, randomly, separated by immense spans of time and distance. But over enough time, the pattern is clear. Atoms lose their identity, then molecules, then any remaining aggregates of matter. What was once solid becomes statistical. The universe no longer contains objects in the familiar sense. Instead, it contains distributions, energy densities. Particle fields, radiation stretched thin across space. As decay proceeds, the difference between matter and radiation blurs. Mass becomes energy, energy becomes wavelength, wavelength becomes scale, everything smooths out. The universe grows more uniform, not because things are mixed together, but because everything is so far apart that distinctions no longer matter. This is not destruction, it is simplification, a gradual release of structure back into fundamental components. At this stage, uncertainty remains an honest part of the story. Physics does not yet know whether protons truly decay, or whether they persist indefinitely. Both possibilities fit within our current understanding. If matter is absolutely stable, then remnants remain forever, cold, inert, scattered. If matter is not stable, then even those remnants eventually dissolve. Either way, the direction is the same. Complexity fades, energy spreads, change slows, the universe becomes increasingly quiet. Whether through decay or through eternal stillness, the outcome converges. There are no objects left that can meaningfully interact, no concentrations of matter capable of sustaining structure, only faint particles, radiation, and space expanding endlessly between them. The distinction between things and space fades, everything becomes part of the same smooth background, and with that, the final sources of structure have passed. The universe has exhaled complexity, and nothing remains to interrupt the calm. Entropy is not an event, it is a direction. It describes how energy behaves when left undisturbed. In every process so far, from stars shining, to remnants cooling, to particles dispersing, entropy has increased, energy has spread out, gradients have diminished, differences have softened. In the final state of the universe, this trend reaches completion. Temperature differences disappear. No region of space is meaningfully hotter or colder than another. There are no stars warming their surroundings, no remnants radiating excess heat, no black holes concentrating energy. Everything approaches the same temperature. Extremely cold, extremely uniform. This state is often called heat death, not because the universe becomes hot, but because heat becomes evenly distributed. Without temperature differences, nothing can happen. No engines can run, no processes can be powered, no work can be done. Motion may still exist, particles may still move, but their motion is random, uncoordinated, without purpose or consequence. Photons continue to travel through space, but their wavelengths stretch with expansion. Each oscillation takes longer than the last. Energy per photon decreases. Eventually, even the faintest radiation becomes indistinguishable from silence. Time continues, but nothing unfolds within it. No events mark its passage, no changes accumulate. The universe does not freeze, it does not stop, it simply rests. A vast equilibrium, where every possible exchange has already occurred, where every gradient has flattened, where entropy has reached its maximum. In this state, the universe is not broken, it is complete. There is nothing left to resolve, nothing left to rearrange. Space continues to expand, but expansion itself no longer produces meaningful change. The universe grows larger, but emptier and quieter. If an observer could exist, there would be nothing to observe, no light sources, no shadows, no contrasts, just uniformity. This is not darkness in the familiar sense. Darkness requires light to contrast against. Here there is only sameness. The universe has become a single, gentle condition, extended across all of space. Time continues without milestones, an endless duration without events. And in this final state, there is no urgency, no tension, no anticipation, only rest. Nothing is waiting to happen. Everything that could happen already has, and the universe remains, calm, complete. There is a quiet comfort in knowing that the universe does not rush. From its earliest moments, through ages of light and structure, and onward into deep stillness, everything unfolds at its own pace. Nothing is hurried, nothing is forced. The end you have been contemplating is not an event to witness. It is a condition the universe gradually settles into. A long rest after an immense journey. What remains striking is not how much is lost, but how gently it all fades. Stars do not scream as they burn out. Galaxies do not collapse in panic. Matter does not shatter in protest. Everything simply follows the path laid out by physical law. Energy spreads. Differences soften. Complexity relaxes. The universe grows quiet because it has finished speaking. And within that perspective, your own moment here becomes clearer. You exist during an era of extraordinary richness, a brief chapter when stars still shine brightly, when chemistry still assembles complexity, when awareness can arise and look outward. This is not something the universe promises to preserve forever. It is something it offers briefly. That brevity does not diminish its value. It gives it shape. Curiosity itself is a feature of this luminous era, a temporary pattern made possible by flowing energy and structured matter. There is no obligation to solve the universe, no requirement to outlast it. Understanding that everything fades does not empty the present. It softens it. The vast future you have been drifting through does not press in on now. It stretches away from it. Trillions upon trillions of years lie between this moment and cosmic stillness. So much time that urgency dissolves, so much distance that anxiety loses its grip. The universe is not counting down, it is unwinding, and you are free to rest within that understanding. Nothing in this story asks you to prepare. Nothing demands vigilance. There are no alarms waiting to sound, no final moments to anticipate, only a calm continuation. As the universe itself eventually releases structure, you can release tension. As energy spreads and smooths, your thoughts can do the same. Breathing becomes easier when there is no need to arrive anywhere. The end of everything is not looming. It is infinitely patient. And in that patience, there is space for rest. You do not need to hold on to the details, the timelines, the physics. They can drift. Like distant stars fading from view, what remains is the feeling of scale, of perspective, of gentle insignificance that comforts rather than diminishes. You are a brief arrangement of matter and awareness, existing during a bright interval, and that is enough. The universe does not require remembrance. It does not need witnesses. It simply continues until there is nothing left to continue. And even then, there is no absence to mourn, only equilibrium. As you settle further into rest, let the immense quiet of the far future mirror a quieter state within you. No expectations, no conclusions, just stillness. Just calm curiosity fading gently into sleep. The universe has all the time it needs, and right now, so do you.